Even with your eyes closed, light can still slip through your eyelids and softly tint what your brain expects. Set your phone face down or dim it and just listen. In a moment, you will hear which invisible kind of light helps set your sleep clock. If you want an easy sleep routine, tap save or add this to a bedtime playlist. That way, you can return anytime your mind feels busy, with no screen needed. Let's begin with a simple map. The electromagnetic spectrum is one long family of light. Some of it is visible, and most of it is quietly invisible to human eyes. All of it is made of ripples in two fields, traveling together through space. One is an electric field, and the other is a magnetic field. They rise and fall in a steady rhythm, like a slow breathing pattern. In a traveling wave, those two fields point at right angles to each other. They also point at right angles to the direction the wave moves. This is why light can cross empty space without needing air to carry it. Sound needs a material to wiggle, but light does not. A vacuum is enough, which is why sunlight reaches Earth across space. Light transports energy without pushing matter along for the ride. A beam can warm a surface, even though nothing material is flowing into it. In a calm way, energy and information can travel without a river of particles. When people say radiation, they often mean this kind of traveling energy. The word radiation is broad, and it can describe both gentle and intense kinds of light. What matters is energy per photon, which depends mainly on frequency. Lower energy light is often called non-ionizing because it cannot easily break electrons free. Higher energy light can be ionizing, meaning it can remove electrons from atoms or molecules. That difference is about physics, not about a scary label. Now, to describe any wave, we can use two linked ideas: wavelength and frequency. Wavelength is the distance from one crest to the next along the direction of travel. Frequency is how many wave cycles pass a point each second. If one goes up, the other goes down in a smooth trade. The connection comes from a single steady speed in vacuum, the speed of light. In calm terms, speed equals wavelength times frequency. So if the wavelength is long, the frequency must be low to keep the same speed. And if the wavelength is short, the frequency must be high. This one relationship lets us translate between different parts of the spectrum. It also explains why radio waves and gamma rays can both be called light. They are not different substances, just different settings on the same dial. The dial can span from waves as long as continents to waves smaller than atoms. Radio wavelengths can be measured in meters or even many kilometers. Visible light wavelengths are tiny, around a fraction of a millionth of a meter. X-rays can be closer to the scale of atoms, and gamma rays can be smaller still. Those scales feel far apart, yet the rules that connect them stay the same. Light in a vacuum moves at a constant speed that does not depend on color. In glass or water, the wave slows down, and that changes how it bends. The frequency stays the same, but the wavelength becomes shorter in the material. That is one quiet reason prisms and lenses can separate colors. Now we add a second language for light, the language of photons. A photon is a single packet of electromagnetic energy. It is not a tiny ball in the usual sense, but a countable unit that can be detected. The energy of a photon depends on frequency, not on brightness. In simple words, photon energy equals Planck's constant times frequency. So higher frequency light comes in higher energy photons. This is why ultraviolet light can trigger chemical changes more easily than infrared light. Ultraviolet photons can nudge certain bonds into new arrangements. Infrared photons are gentler per photon, and they often show up as heat. Brightness is a different idea from photon energy, and it can be easy to mix them up. Brightness is about how many photons arrive and how much total energy is delivered. You can have a very bright infrared lamp with low energy photons arriving in huge numbers. You can also have dim ultraviolet light with higher energy photons arriving more sparsely. The wave picture and the photon picture are both useful depending on the question. When you measure light in very small amounts, photons become hard to ignore. When you describe spreading and bending and interference, waves feel more natural. Most of the time, both pictures meet in the middle without any conflict. Even when we talk about particles, light can still spread out and make interference patterns. Even when we talk about waves, detectors can count individual arrivals like soft taps in the dark. Now, humans divide the spectrum into named bands as a practical habit. We say radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. These names help engineers, doctors, and scientists speak efficiently. But nature does not draw sharp borders between them. The edges blur and the band labels can overlap depending on the context. Microwaves are often defined by how we generate and use them, not only by wavelength. X-rays and gamma rays can overlap too, especially when you compare different sources. Sometimes the label comes from how the radiation was produced, not just its energy. That is a gentle reminder that our categories are tools, not walls. Another useful idea is the atmosphere, which acts like a selective filter. Some wavelengths pass through the air easily and others are absorbed high above. Visible light travels well through the sky, which is part of why eyes evolved to use it. Radio waves also have broad windows that can reach the ground. But much of the ultraviolet is blocked, protecting surface life from harsh exposure. X-rays and gamma rays are also mostly blocked, which is quietly helpful for biology. Infrared is partly absorbed by water vapor and other gases, but some bands get through. These open passages are called atmospheric windows, like calm clearings in a forest. To see the blocked bands clearly, astronomers often use telescopes above the atmosphere. Space telescopes are not just for higher resolution, but for access to hidden wavelengths. Different wavelengths reveal different stories about the same object. Visible light shows starlight and reflected light, which feels familiar. Infrared can show warm dust and cool stars that hide behind clouds. Radio waves can map cold gas and magnetic structures across galaxies. X-rays can highlight very hot gas like the thin plasma around black holes and clusters. Gamma rays can point to extreme events, where particles are pushed to high energies. So the spectrum is like a multi-layer portrait, each band adding a quiet detail. Now, how do we make electromagnetic waves in the first place? A simple answer is accelerate an electric charge, and it can radiate energy outward. An antenna does this with electrons moving back and forth, creating radio waves. In a microwave oven, an electronic device generates microwaves that stir water molecules. In a hot filament or a warm stone, thermal motion produces a broad glow across wavelengths. Everything with a temperature above absolute zero emits some electromagnetic radiation. Cool objects emit mostly long wavelength radiation, while hotter objects shift shorter. This is why infrared cameras can find warm animals in a dark scene. Atoms and molecules also emit and absorb light in distinct transitions. Electrons can jump between energy levels, releasing photons of specific frequencies. Molecules can rotate and vibrate, making lines in the microwave and infrared ranges. These patterns act like fingerprints, letting us identify substances from far away. Now, detection is the other half of the story, and it depends on the band. A radio antenna detects waves by letting them drive a current in the metal. Infrared detectors can measure tiny warming using sensors that respond to heat. Visible light detectors, like photodiodes, convert photons into electrical signals. Some detectors use materials that flash faintly when struck, then measure that flash. Those are used for higher energy radiation, where each photon carries more punch. Across all of these, the goal is the same: translate light into a readable signal. And under it all, the spectrum remains one continuous set of electromagnetic waves. Here is a soft question to hold as we go on. If you had to guess, what % of the whole spectrum can your eyes actually see? Is it tiny, medium, or large compared with everything else? With that map in mind, we'll step into the narrow slice your eyes call color. Now we step into the narrow slice your eyes call visible light. It is a small neighborhood inside a much larger spectrum. Most light in the universe is invisible to us, even when it is all around. Visible light is not a separate substance, just a band our biology can detect. As a working range, Think of about 380 to 740 nanometers. That range is a helpful map, not a hard fence. Different people may notice slightly different edges of that band. At very low brightness, the edges feel different than in daylight. As light gets dim, your color sense softens and details change first. Part of that is because your eyes switch which cells do most of the work. In brighter light, cone cells guide color with steady precision. In dim light, rod cells take over and color becomes quieter. This is why a deep red can look rich in daylight, then fade at night. So even inside the visible band, your experience can shift with context. Here is the first gentle payoff from our spectrum map. The slice you see is tiny compared with everything that exists. If you imagine the full spectrum as a long coastline, visible light would be a short cove. So why did vision settle on this cove at all? One reason is practical sunlight and a practical atmosphere. Our sun sends out a broad spread of wavelengths. But Earth's air is selective, like a calm filter. A lot of visible light passes through the sky well enough to be useful. Some ultraviolet is blocked higher up, and that matters for surface life. Many longer infrared bands are absorbed by water vapor and other gases. So the visible window is not only about the sun, but also about the air we live in. Another reason is energy balance inside living tissue. Visible photons carry enough energy to be detected cleanly, but they are usually not so energetic that they break molecules easily. That sweet spot makes sensing light safer and more stable for biology. Even so, visible is not a single thing you can hold. It is a range of wavelengths your nervous system interprets as color. And color is a measurement, not a mood. The feeling that a color has a mood comes later from memory and meaning. First, there is physics. Wavelength mixtures arriving at your eyes. A single wavelength is sometimes called monochromatic light. A laser pointer is close to monochromatic, though not perfectly pure. Sunlight is not monochromatic at all. Sunlight is a thick blend of many wavelengths traveling together. A white wall looks white because it sends many wavelengths back to you at once. Your brain calls that blend white because it is balanced enough to feel neutral. A blue wall looks blue because it sends more short wavelengths back than long ones. A red apple looks red because it reflects more long wavelengths and absorbs many others. So color often begins as a filtering story. What gets absorbed and what survives. Now consider a screen like a phone or a television. A screen makes color by adding light, not by absorbing it. This is called additive mixing. Tiny red, green, and blue lights blend into a single impression in your eyes. When all three are strong together, you perceive a kind of white. When only red and green are strong, you perceive yellow, even though no yellow wavelength is required. That is a key idea. Your eyes do not measure a full spectrum with perfect detail. They sample the spectrum through a small number of cone types. So many different spectra can produce the same cone responses. This is called metamerism, and it is quietly everywhere. Two lights can be physically different, yet look identical to you. A white light from the sun and a white light from an LED can match in appearance, but their spectra can be shaped very differently underneath. Your eyes mostly care about the pattern of stimulation, not the full fingerprint. Now switch to paint, ink, and colored fabric. Pigments make color by subtracting, not adding. This is called subtractive mixing. A pigment absorbs certain wavelengths and leaves others to be reflected. Mixing pigments often means you absorb more and reflect less. That is why mixed paints tend to darken and become more muted. With light on a screen, mixing tends to brighten. With pigments on paper, mixing tends to deepen and soften. So the same words like mixing colors can hide two opposite mechanisms. Now for a calm little surprise. Some colors you can see do not correspond to any single wavelength at all. Pink is a classic example. There is no single pink wavelength in the spectrum. Pink is your brain's way of interpreting a mix, often red with some blue and less green. It is a useful label for perception, not a simple point on the wavelength line. Purple can also be a perceptual bridge between spectrum ends. Your brain stitches the ends together into a loop of experience. This is why artists talk about a color wheel. even though the physical spectrum is a line. The wheel is a map of perception, not a map of wavelengths. If you are listening in bed, you can hold a soft image. Imagine a long piano keyboard of wavelengths. Now imagine your brain pressing several keys at once and calling it one color name. That is close to how mixtures work in everyday life. Now let's talk about brightness in a gentle and practical way. Brightness is not simply more watts. Watts measure radiant power, the raw energy per second. Your eyes do not respond equally to every wavelength in that energy. Human daylight vision is more sensitive to some wavelengths than others. In bright conditions, it is most sensitive around the green to yellow region. So a green light can look brighter than a deep red light, even at the same radiant power. This is why lighting uses special units that are weighted to human vision. A lumen is radiant power adjusted by how bright it appears to the average human eye. Lux is lumen spread over an area, like how much light lands on a surface. Candela describes intensity in a particular direction, like a beam's concentration. These units are not more real than watts, just more human-friendly. They measure light in the way our eyes care about it. If you have ever dimmed a lamp and noticed a slow change, that is normal. Your perception of brightness is not a straight line. A small drop at high brightness can feel subtle. A small drop at low brightness can feel large. Your visual system adapts, and it is always recalibrating. In a dark room, a phone screen can feel strong, even at low power. In sunlight, the same screen can look weak and washed out. So brightness is a relationship between light and adaptation, not an absolute feeling. There is also a shift between daylight and nighttime sensitivity. As it gets darker, your rods become more important. Rods are more sensitive to blue-green than to deep red. So in dim light, blue-green can appear relatively brighter than red. This is one reason twilight scenes can feel cool in tone. It is not only the world changing, but also your eyes' weighting changing. Now we move from measurement to geometry, still staying calm. Let's talk about rainbows in a slow, predictable way. A rainbow begins with light entering a drop of water. The light bends as it enters because it slows inside the water. Then it reflects inside the drop like a soft internal mirror. Then it bends again as it leaves the drop back into air. Because the bending depends slightly on wavelength, the colors spread out. This spreading is called dispersion. A prism does the same basic thing with glass instead of water. Raindrops are like countless tiny prisms hanging in the air. When conditions are right, each drop sends a little colored fan back toward you. From your point of view, those fans line up into an arc. The arc is part of a full circle. You usually see an arc because the ground blocks the lower part of the circle. From an airplane, people sometimes see a fuller ring because the view is open. So a rainbow is not over there sitting on a hill. It is a viewing angle that depends on where you are. If you move, the rainbow moves with you. That can feel magical, but it is simply geometry and many droplets doing the same job. Sometimes you see a second, fainter rainbow outside the first. That outer arc comes from an extra internal reflection inside the droplets. Because of that extra bounce, the color order reverses. The second arc is usually dimmer because more light is lost on the way out. Between the two arcs, the sky can look slightly darker. That darker band is a quiet gap where fewer rays reach your eyes. None of this requires drama. It is just light taking slightly different paths, then meeting your viewpoint. Now let's look upward toward the everyday sky. The daytime sky is blue for a reason that is both simple and deep. Air molecules scatter shorter wavelengths more strongly than longer ones. So blue light is redirected across the sky in many directions. When you look away from the sun, you see that scattered blue light coming toward you. If the air is very clean, the blue can look deeper and more saturated. If the air has haze, smoke, or dust, the scattering changes. Larger particles scatter more evenly across wavelengths. That can wash the sky toward pale blue, gray, or milky white. So the sky color is a gentle report about what is in the air. Now consider sunset when the sun is low. At sunset, sunlight travels a longer path through the atmosphere before reaching you. Along that longer path, more short wavelength light is scattered away. The direct light that remains becomes richer in longer wavelengths. That is why sunsets tend to warm toward orange and red. Clouds can catch that warmed light and glow softly, and aerosols can make the color shift stronger, sometimes deepening reds. This is not the sky changing moods. It is light being filtered by distance and particles. Now, a small, calming clarification about moonlight. Moonlight is just sunlight reflected from the moon. Its spectrum is similar to sunlight, though slightly modified by reflection. But moonlight usually looks cooler and dimmer mainly because it is faint. At low intensity, your night vision changes the way color feels. So the moon can seem silvery or bluish, even though it is borrowed sunlight. The story is partly physics and partly your own adaptive eyes. Now we add a hidden property that many people forget exists. Light has polarization, which is like an orientation of its wave oscillation. For unpolarized light, that orientation is mixed and shifting. For polarized light, the oscillation has a preferred direction. You cannot feel polarization directly, but you can filter it. A polarizing filter is like a quiet gate that favors one orientation and blocks others. This is why polarized sunglasses reduce glare. Glare from water, roads, and glass is often partly polarized by reflection. When the filter is aligned, reflections soften and the scene feels calmer. If you want a gentle mental image, imagine slowly rotating a filter in front of your eyes. As you rotate, bright reflections fade, then return in a slow cycle. That fading is polarization becoming visible through a tool. The sky itself also has polarization patterns. Scattered sunlight becomes partially polarized across the sky. The pattern depends on the sun's position, even if you cannot see it. Some animals can sense this pattern and use it for navigation. Many insects can detect polarized light with special structures in their eyes. Some birds also appear to use sky cues that include polarization information. For them, the sky can contain a faint, organized map that humans mostly miss. This is one quiet hint of a larger theme. The world contains more visual information than our eyes were built to sample. Now return to color as measurement, not mood. Once your brain labels a color, it can attach meaning. Deep blue can feel like night, distance, and quiet water. Soft amber can feel like firelight, shelter, and late afternoon. Neutral white can feel clean and clear, like daylight on a plain wall. Those feelings are real experiences, but they are not stored inside the photons. They come from learning, memory, culture, and a little physiology. Here is a gentle interaction to keep your attention without waking you up. Which feels calmer to you right now? Deep blue, soft amber, or neutral white? You do not need to answer out loud. Just notice your first instinct and let it sit. In the next section, we will explain why those preferences can make sense inside the brain. For now, the main idea is simple and steady. Visible light is a narrow band, and color is a code your eyes create from it. It can be measured, mixed, filtered, bent, and scattered. And yet, it can still feel personal because your brain finishes the picture. Now that color is grounded in physics, we can turn to the quiet interpreter behind it. We will move to your eyes and brain and how other creatures do it differently. Seeing starts with photons, but it does not end there. Your eyes collect light, and your brain turns it into a steady world. That translation is not a flaw. It is a quiet survival skill. The brain is always guessing, and most of the time it guesses well. It builds a scene that feels stable, even when the input is messy. Inside your retina, two main kinds of sensors share the work. Cones handle fine detail and most of your color sense. Rods are built for dim light, when every photon matters. In bright daylight, cones lead the story. In a dark room, rods slowly take over. That handoff is why colors fade at night. It is not that color stops existing. It is that your night system is not designed to label it precisely. Rods are very sensitive, but they do not separate wavelengths the same way cones do. So the world becomes more about shapes, edges, and motion. If you have ever noticed reds disappearing first in low light, that fits the pattern. Your visual system is changing modes, like a calm shift into nighttime settings. This shift takes time, and it is driven by chemistry, not willpower. Dark adaptation is a physical process inside the retina. Light-sensitive molecules need time to reset after being used. In bright light, they are quickly bleached and recycled. In darkness, they rebuild and become ready to catch faint light again. That is why stepping into a dark room feels slow at first, and why it feels easier a few minutes later. It is also why a sudden bright screen can feel so strong at night. It interrupts that rebuilding process with a single burst. If you are listening in bed, you may have felt this without naming it. Now consider afterimages, those gentle ghost colors that linger. An afterimage is often your system recalibrating after intense stimulation. When one set of sensors is strongly activated, the brain temporarily balances against it. So you can look away and still feel a faint opposite tint. It is like a quick correction that overshoots, then settles. Not a supernatural echo, just a short-lived adjustment. Even a simple bright shape can leave a soft imprint for a moment. Your brain is always normalizing, trying to keep perception stable. This is one reason you can stare at a white wall and still feel it as white. Your system is tuned to contrast and change, not perfect measurement. Now, a loop back to our opening idea. Light can reach you even with your eyes closed, and that is literal. Your eyelids block a lot, but not all. They are a soft filter, not a perfect door. If a phone screen is bright in a dark room, some of that glow can still pass through. Many people notice a warm reddish tint through closed lids. That happens because skin and tissue tend to pass longer wavelengths more easily than shorter ones. So blue light is reduced more than red, even before it reaches your retina. But reduced does not mean absent. A bright screen can still feel like daylight to parts of your visual system. This is why it can feel bright even when you are not looking directly. You do not need to be staring to be affected by a glow in the room. A simple self-check is gentle and easy. Place your phone face up on the bed, then close your eyes for a moment. Now place it face down or cover it and notice the difference. Most people feel the room settle when the direct glow is removed. That difference is not imagination. It is the amount of light reaching you, even through lids and scattered reflections. This is not meant to worry you. It is meant to give you a calm lever you can use. Small changes in light placement can change how the room feels. Now we move from brightness to interpretation. Your brain does more than detect light. It tries to identify objects under changing conditions. One key trick is color constancy. Color constancy is why a white shirt stays white in many kinds of lighting. Morning sunlight can be cool. Indoor lamps can be warm. And yet the shirt usually reads as the same shirt. Your brain estimates the color of the light source and corrects for it. It is like a quiet, automatic white balance. This helps you recognize things quickly without extra effort. It also makes the world feel predictable. Predictability is calming because it reduces mental work. You do not have to relearn a room every time the light changes. Cameras struggle with this unless they are carefully calibrated. A camera sensor records raw proportions of light reaching it. Your brain records meaning like paper and skin and shadow. So a camera can show a scene that feels wrong, even when it is physically accurate. That mismatch is a reminder that seeing is an interpretation. It is a calm story your nervous system tells, based on evidence. Now, optical illusions can fit into this same idea. An illusion is often a shortcut being revealed. Your brain uses patterns that usually work because they save time and energy. It favors edges, contrast, and motion cues. It often cares less about absolute brightness values, so a shaded shape can look like it changes color even if it does not. Or a static pattern can seem to drift when your eyes move slightly. This can happen more in low light, when the input is noisy. In dim conditions, ambiguity increases and the brain fills in more. That is not a defect. It is an efficiency strategy. If a faint shadow looks like a shape for a second, your system is exploring possibilities. You can treat that as a gentle curiosity, not a threat. Notice it, then let it pass. The brain is trying to help, even when it guesses wrong. Another quiet shortcut is that your visual system samples in time. Your eyes make small movements constantly, even when you think you are still. The brain stitches those samples into one stable picture. Most of the stitching is invisible to you. That is why the world does not blur every time you blink. Now we add a deeper layer that is not about images at all. Light also sets your daily timing. Your body uses light as a schedule cue. This is your circadian rhythm, a roughly daily cycle. A special set of light-sensitive cells in the eye report brightness to the brain. They are not mainly used for forming sharp images. They are used for timing, like a quiet clock signal. These cells respond strongly to blue-rich light. That matters because daylight has a lot of blue content, so morning light can tell the body, this is the start of the day. Over days, that regular cue can stabilize sleep patterns. At night, dimmer and warmer light gives a different message. It says this is a low activity time. Timing matters more than drama. Small, consistent cues add up. A short walk in morning light can be more helpful than one intense burst at a random hour. And a darker room at night can support the body's natural wind down. This is not about perfection. It is about gentle trends that the nervous system can follow. We will revisit light and timing again when we talk about warmth and sunlight later. For now, just keep the idea that light is both a picture and a signal. Now, hold a low stimulation question as you listen. If you could add one extra sense, which would feel more useful? Ultraviolet patterns or infrared warmth? You do not need to decide firmly. Just notice which one your mind leans toward, because many creatures already live in worlds like that. Some snakes can sense infrared warmth with specialized organs. They can build a rough heat map of nearby prey, even in darkness. It is not like a perfect thermal camera, but it is enough to guide a strike with quiet precision. Bees can see into ultraviolet. Many flowers have ultraviolet patterns that guide pollinators. To us, those patterns are invisible, but to a bee, they can be like runway lights. Some birds also detect ultraviolet, adding an extra channel to their color world. That can change how feathers look and how mates are chosen. In the ocean, light changes with depth. Water absorbs red light quickly, so reds fade first as you go down. Deeper down, the world becomes blue-green, then darker still. Deep-sea creatures often tune their eyes to the wavelengths that remain. Some even make their own light, matching the colors that travel farthest underwater. That is one reason bioluminescence often looks blue-green. It is a practical choice in a watery world. Now, a quick myth check that is worth keeping calm. You may have heard that mantis shrimp see more colors than we can imagine. They do have many types of light receptors, but their brains appear to process color differently than ours. Instead of mixing signals for fine color comparison, they may classify colors quickly. It is like having many labeled bins rather than one delicate measuring ruler. So the story is not simply more receptors equals richer experience. It is different receptors, different strategy. Across nature, perception is a set of trade-offs. Sensitivity versus detail, speed versus precision, energy cost versus information gained. Your own vision is one solution among many, and it is tuned to a life on land under a bright sun in a filtering atmosphere. When you lie in the dark, your system shifts into its nighttime version. Colors soften, edges matter, and small lights feel large. That is the same system doing its job, not doing it wrong. If you want a gentle comfort thought, you can use this. Your brain is always trying to reduce uncertainty. That effort is why the world feels stable most of the time. And when you rest, you can let that effort ease. Now, one last small link back to your room. If your screen is on, it is not only an image, it is a timing signal and a brightness signal. So if you want the room to feel calmer, reduce that signal. Face down, dimmed, or out of reach can be enough. No struggle, just a small adjustment. In the next part, we drift out of visible light into the longest, slowest waves. We will enter radio, where information can ride across oceans and across space. Before we drift into the next chapter, take a small, gentle reset. If you are in bed, let the room do less work for your brain. Lower your screen brightness until it feels almost unnecessary. If you can, place your phone face down or slightly out of view. Keep the audio steady and let your eyes rest without chasing light. If you are wearing headphones, loosen them a touch so nothing feels tight. If you are using a speaker, set it just low enough that you do not strain to hear. Now take one slow breath in and a slow breath out. Nothing to achieve here, just a softer baseline. If you want a tiny way to bookmark tonight, you can leave one word in the comments. Choose the one you feel most curious about right now: radio, infrared, or space. Just a single word is enough, and you can do it now or later. Then you can return to listening without needing to watch anything. All right, radio waves first, slow and wide, and surprisingly close to everyday life. Radio waves are light, just stretched into very long wavelengths. They carry low energy per photon, which is one reason they do not ionize atoms. If visible light is a tight violin string, radio is a slow, wide bass note. You cannot see radio waves, but you live inside them every day. They pass through air easily, and many pass through walls as well. A simple way to picture a radio wave is as a gentle rolling field. It is not a push of air, like sound. It is a traveling pattern of electric and magnetic change. Radio waves are often made by moving electric charges back and forth. An antenna is, in a quiet way, a place for electrons to sway in rhythm. When the rhythm is steady, the antenna releases energy outward as a wave. The wave moves away, spreading out as it travels. As it spreads, the same power covers a larger and larger area. That is why signals fade with distance, even in empty space. A calm rule of thumb is that strength drops fast as you get farther away. If you double your distance, the energy is spread over about 4 times the area. So distance is a powerful dimmer for radio signals. This fading is not failure, it is geometry. The wave is simply sharing itself with more space. A radio receiver is another antenna listening for that rhythm. The incoming wave nudges electrons in the receiving antenna. Those tiny nudges become a tiny voltage, like a whisper in a wire. Then circuits amplify that whisper into something usable. Because radio is gentle per photon, it often needs sensitive receivers. This leads to another quiet fact. The universe is never perfectly silent. Even in deep space, there is background radio noise. Some noise comes from the receiver itself, because warm electronics jitter. Some noise comes from Earth's atmosphere and weather. Some noise comes from the sun and from distant cosmic sources. So radio is always a listening game with a soft hiss in the background. Engineers talk about a noise floor, the level you cannot go below. To be heard, a signal must stand above that floor in some way. Sometimes it is by being stronger. Sometimes it is by being clearer, like a well-shaped pattern. This is where modulation enters the story. Modulation means placing information inside a wave. A radio system often begins with a steady carrier wave. Think of the carrier as a calm, repeating heartbeat. Then the message gently changes that heartbeat in a controlled way. One style is amplitude modulation, often called AM. In AM, the wave's height rises and falls to match the message. If the message is music, the carrier's height follows the music's shape. This works well, and it is historically important. But changes in height are also easy for random noise to imitate. So AM can sound crackly when conditions are poor. Another style is frequency modulation, often called FM. In FM, the carrier keeps a more constant height. Instead, the wave's timing shifts slightly faster or slower. Those tiny shifts encode the message without relying on height alone. Because many noise sources mainly disturb height, FM can resist some noise better. This is why FM often sounds cleaner in everyday listening. Both AM and FM are ways to hide meaning inside rhythm. Neither one is magic, and neither needs heavy math to understand. They are like two handwriting styles for the same sentence. Now, modern communication often uses digital modulation. Digital modulation still rides on a carrier wave, but the information is arranged in structured steps and patterns. Instead of smoothly changing the wave, the system selects among defined states. It is like a calm set of choices, repeated quickly and precisely. The receiver looks for those choices and reconstructs the message. This can be very efficient, especially when signals are weak. It can also allow error correction, like gentle self-checking. So digital radio is not more dramatic, just more organized. Now let's lift our view upward, toward the air above the air. High above you is a region called the ionosphere. In that region, sunlight can knock electrons free from some atoms. This creates layers of charged particles in the upper atmosphere. Those layers can bend and reflect certain radio frequencies. It is not like a hard mirror. It is more like a slow refraction, a curved path through a changing medium. Still, the effect can be strong enough to send signals far beyond the horizon. This is why shortwave radio can travel surprising distances. A signal can rise, meet an ionospheric layer, then return to Earth farther away. It can bounce again, stepping across oceans in quiet hops. The ionosphere changes between day and night. During the day, sunlight strengthens ionization and reshapes the layers. At night, ionization decreases and the structure relaxes. So radio propagation can improve or worsen depending on time and frequency. This is why some distant stations are easier to hear after sunset. The sky becomes a different radio environment as darkness arrives. Space weather can also play a role. When the sun is active, it can stir the ionosphere in complex ways. Auroras are one visible sign of those disturbances, and auroral activity can change how radio waves travel. Sometimes it adds noise. Sometimes it bends paths differently. It is a gentle reminder that radio is part of a larger Earth and space system. Now bring radio back down to your daily life. Your phone is a small radio, and it uses several bands and methods. So does your wireless router. So do many remote controls, sensors, and key fobs. Bluetooth is a short-range radio link that trades distance for convenience. It uses low power and clever protocols to avoid collisions. Cellular networks use radio links too, but coordinated by towers and timing. Even when you are not calling, your phone may check in quietly. It listens for signals, and it sometimes transmits small updates. This is why you can sometimes hear a faint buzz in nearby speakers. It is not the speaker hearing sound from the phone. It is the speaker's electronics picking up radio energy and turning it into a hum. It is like eavesdropping on the edge of radio life. Not every speaker does this, and not every phone creates the same pattern. But if you have noticed it, you have sensed radio indirectly. Now, buildings and materials can change reception. Metal can reflect and block radio waves strongly. Concrete can weaken signals, especially at higher frequencies. Water can absorb some radio bands, and even your body contains water. That is why moving a phone a few centimeters can change signal quality. In a room, radio waves can bounce and interfere with themselves. A signal can arrive by several paths at once, each with different timing. Sometimes those paths add together and strengthen reception. Sometimes they cancel and create a quiet dead spot. This is called multipath, and it is common in cities and indoors. It is one reason your connection can feel moody even when nothing else changes. Now, a practical bedtime detail, framed calmly. Airplane mode reduces your phone's radio transmissions. It tells the device to stop cellular, Wi-Fi, and Bluetooth unless you re-enable them. It does not remove stored light from the screen, of course, but it can reduce the steady background of transmissions in the room. For many people, it is simply a quiet habit, like closing a door. Now let's talk about the Global Positioning System, often called GPS. GPS is usually explained as location, but timing is the deeper heart. Satellites carry very accurate clocks. They send time-stamped radio signals down to Earth. Your receiver compares arrival times from several satellites. From those timing differences, it computes distance and then position. So you can think of GPS as a set of flying clocks, whispering time. Location comes from time, measured with great care. That is a beautiful radio idea, a map made from rhythm. Now we drift outward into radio astronomy. Radio telescopes do not look for light with eyes. They listen for radio energy collected by dishes and antennas. A radio dish is like a quiet ear, shaped to focus waves onto a receiver. Many radio sources in space are cold, not hot, and bright like stars. Clouds of gas can be very dark in visible light, yet loud in radio. One famous example is neutral hydrogen. Hydrogen atoms can emit a very specific radio wavelength. It is called the 21 centimeter line. It comes from a subtle change in the hydrogen atom's internal state. Because hydrogen fills galaxies, that line can map structure across enormous distances. It lets astronomers trace spiral arms and hidden gas. Radio can also reveal magnetic fields through polarization effects, and it can show energetic particles spiraling in those fields. Some of the most steady radio beacons are pulsars. A pulsar is a rapidly rotating neutron star. It emits beams that sweep through space like a lighthouse. When the beam crosses Earth, we detect a pulse. Some pulsars are so regular they behave like precise clocks. They can teach us about gravity, dense matter, and space-time itself. In a calm way, radio lets us time the universe. Now, one dish can listen, but many dishes can listen together. This is called interferometry. It combines signals from antennas spread far apart. Together, they act like one much larger telescope. Not by building a giant solid dish, but by linking many smaller ones. The result is sharper detail, like better focus for radio vision. It is teamwork turned into resolution. Radio astronomy also connects to a quiet relic of the early universe. There is a faint background glow that fills space. It is strongest in the microwave range, close to radio. It is like leftover light from a much hotter early time. We will talk more about that in the next chapter on microwaves. For now, just keep the idea that radio can carry ancient information. It can be old light, stretched by the expansion of space. Now let's speak gently about safety and exposure in everyday life. Radio waves in typical environments are regulated and measured. A common measurement idea is specific absorption rate. It is often shortened to SAR. SAR describes how much radio energy is absorbed by tissue under defined conditions. It is not a mood, it is a test setup and a number. In daily life, distance is one of the biggest factors. Very close to a source, fields can behave differently than far away. This is sometimes described as near field versus far field. Near field is close, where the geometry is complex. Far field is farther, where waves spread more cleanly. For most simple sources, stepping back even a little reduces exposure a lot. Power level matters, distance matters, and time matters. So context prevents worry spirals. A low-power device across the room is not the same as a high-power transmitter nearby. Most personal devices are designed to operate within exposure limits, and public guidance is built around wide safety margins. So the calm approach is simple. Use devices normally, follow basic instructions, and let the background fade into ordinary life. Radio is, in many ways, the quiet infrastructure of modern living. It carries voices, music, data, timing, and discovery, and it does it with long waves and gentle photons. Next to radio sits the microwave band. It is familiar in kitchens, essential in weather maps, and echoing from the early universe. Microwaves sit next to radio on the spectrum, just a bit shorter and quicker. They are still low energy per photon, and they are still non-ionizing in typical uses. What changes is how easily we can use them to interact with matter. In a kitchen, microwaves are famous for one job: gentle heating. They heat by nudging certain molecules to move in a repeating rhythm. Water is the star here, because it is a strong electric dipole. A dipole is a molecule with a slightly positive side and a slightly negative side. In a microwave field, that dipole tries to turn back and forth. It is like a compass needle, but for electric orientation instead of magnetic direction. The field flips direction rapidly, and the molecules keep trying to follow. That repeated turning becomes friction-like motion among neighboring molecules, and that motion shows up as heat in the food. So the heating is energy transfer, not a special kind of leftover substance. A calm myth check is useful here. Microwaves do not stay stored inside food after the oven stops. When the power stops, the field stops and the pushing stops. What remains is only the warmth that was transferred during heating. Many ovens use a frequency around 2.45 gigahertz. That choice is practical, not magical. It interacts well with water-rich foods, and it fits a common shared frequency band. But even at that frequency, heating is rarely perfectly even. Microwave ovens create standing wave patterns inside the cavity. A standing wave is where peaks and valleys of field strength stay in place. So one spot can get more energy, while a nearby spot gets less. That is why some bites come out hot, and some feel cooler. The turntable is a simple solution. It moves the food through different parts of the pattern. Stirring is another solution because it redistributes heat by mixing. And resting time matters because heat continues to spread after the field is gone. The center warms as energy conducts inward, even after you stop heating. So the oven is not only about waves, but also about ordinary heat flow. Now let's picture the inside of the oven without any drama. Think of ripples in a small contained pond. The pond has walls, so ripples reflect and interfere. A microwave cavity does the same thing with electromagnetic waves. The metal walls reflect microwaves efficiently. That reflection keeps energy bouncing around until it is absorbed by the food. Microwaves enter the cavity through a channel called a waveguide. A waveguide is like a hallway designed for waves instead of people. It steers the energy from the source into the cooking space. Inside the cavity, geometry matters. Corners, edges, and object shapes can change the pattern of hot and cool zones. Now look at the door with its dark mesh window. The mesh is a quiet piece of engineering. The holes are small compared with the microwave wavelength. So microwaves cannot pass through easily, but visible light has a much shorter wavelength, so it can pass through those holes. That is why you can see your food, while the microwaves stay contained. The door also has seals and interlocks, designed to keep leakage low. So the oven is a contained wave space with very ordinary physics. Waves reflect, waves interfere, and water-rich molecules absorb energy into heat. Now we broaden the idea beyond the kitchen. Microwaves are also used to see when eyes cannot. This is the world of radar. Radar works by sending out a microwave signal and listening for its return. If a pulse goes out and comes back, the time delay tells distance. It is a quiet echo, measured with careful timing. If the returned signal shifts slightly in frequency, that can indicate motion. That shift is called the Doppler effect. The same idea that changes a passing siren can change a returned microwave tone. So radar can measure movement without touching anything. Ships and aircraft have used radar to navigate through fog and darkness. Weather services use radar to map rain and storm structure. Raindrops and ice scatter microwaves in detectable ways. So a weather radar picture is a map of reflections translated into patterns. It can show bands of rain swirling motion and where storms are building. That data becomes calm guidance, where to expect showers and when to take shelter. Microwaves can be practical even when the sky is visually dull. Now we step back into everyday convenience again. Wi-Fi is also microwave communication. Many home networks use bands around 2.4, 5, and 6 gigahertz. These numbers describe the carrier frequency range, not the content of your data. The trade-off is gentle and predictable. Lower frequency bands tend to travel farther and penetrate walls a bit better. Higher frequency bands can carry more data, but they fade faster with distance. They also struggle more with obstacles. Water absorbs microwaves, so bodies, plants, and even humid air can reduce signals. That is why a router can feel strong in one room and weak in another. The signal is not only fading, it is also bouncing and interfering indoors. Crowded airwaves can slow things down too. If many devices share the same band, they take turns to avoid talking over each other. That creates delays that feel like buffering or lag. The calm response is not worry, just placement and routine. A router in a central, open spot often works better than one tucked behind furniture. At night, your routine can focus on quieting notifications, not fearing the waves. If it helps you relax, you can turn off Wi-Fi or use airplane mode while you sleep. Not because you must, but because a quieter device can feel like a quieter room. Now we drift up to satellites, where microwaves become a tool for remote sensing. Remote sensing means measuring Earth without touching it. Visible light satellites are like cameras, and they are easily blocked by clouds. Microwaves can do something different. Many microwave wavelengths can pass through clouds far better than visible light. So satellites can observe day or night, clear or cloudy, in useful ways. Some instruments are passive. They simply listen to the natural microwave glow from Earth. That glow depends on temperature, moisture, and surface texture. So passive microwave data can help estimate soil moisture. It can track sea ice and snow properties. It can sense changes over oceans that relate to winds and waves. Other instruments are active. They send a microwave pulse and measure the reflection. This includes radar altimeters that measure sea surface height, and imaging radars that map land and ice with high detail. One powerful method is synthetic aperture radar. It uses motion and timing to build a sharp image from many echoes. The result can reveal fine structure even in darkness and cloud cover. In a calm way, microwaves let us read texture and moisture from orbit. They turn the planet into a quiet pattern of signals. Now we go even higher, beyond Earth entirely. There is a microwave glow that fills the whole sky. It is called the cosmic microwave background. It is not coming from one place. It is a nearly uniform bath of microwaves arriving from all directions. It is often described by a temperature of about 2.7 Kelvin. That is a way to describe its energy, as if space itself has a faint warmth. This glow is a leftover afterglow from the early universe. Long ago, the universe was much hotter and denser. Light could not travel freely because matter kept scattering it. Then the universe cooled enough for light to decouple and stream outward. As space expanded over time, that light stretched into microwaves. So, when we detect it, we are sensing very old light, softened by cosmic time. It is one of the oldest signals we can measure directly, and it is remarkably even across the sky. But it is not perfectly smooth. Tiny variations exist, like faint ripples in brightness. Those tiny variations are fingerprints of early structure. They relate to small differences in density that later grew into galaxies and clusters. So microwaves tell two stories at once. They can warm your soup in minutes, and they can carry an ancient whisper from the beginning of the cosmos. Here is a gentle bedtime question to hold. If you could see heat as colors, would that feel soothing or distracting? Some people find it calming to imagine warmth as a soft gradient. Others prefer the simplicity of not seeing it at all. Either answer makes sense, because attention itself has a cost. Next, we slide into infrared. It is light you mostly feel as warmth, and cameras can translate into calm images. Infrared light begins just beyond the red end of visible color. It is still electromagnetic radiation, just with longer wavelengths than red. You cannot see it with your eyes, but you can often feel its effects as warmth. A simple grounding cue is this. Notice any warmth you feel right now in your hands, your face, or under a blanket. That sensation has a light-based story. Most everyday warmth is carried by infrared radiation. When people say heat vision, they usually mean infrared vision. Thermal cameras do not see temperature directly. They detect infrared light emitted by objects and translate it into a picture. Infrared is often divided into near, mid, and far bands. Those labels are practical because different detectors and materials work best in different ranges. Near infrared sits closest to visible light. Far infrared is closer to microwaves and feels more like broad, gentle heat. Mid-infrared is where many molecules have strong vibration fingerprints. Now, the key idea is simple. Anything with a temperature above absolute zero emits electromagnetic radiation. The spectrum of that emission depends on temperature. At ordinary room temperatures, much of the emission is in infrared. That includes you. Humans radiate infrared continuously, even in total darkness. You are, in a quiet way, glowing all the time. It is not a bright glow to a thermal camera, but it is clearly detectable. As temperature rises, the total emission increases. And the peak of the emission shifts toward shorter wavelengths. This shift is one of the most useful stories in physics, and we can hold it gently. Think of temperature as having a light language. Hotter objects speak in shorter wavelengths. Cooler objects speak in longer ones. The details can be complex, but the direction is steady. A concept that helps is the idea of a blackbody. A blackbody is an ideal emitter and absorber of radiation. It is a reference model, not a perfect real object. Many real things approximate it in broad shape, especially when they are not shiny. Stars, for example, often look roughly like blackbodies in their overall color. Then, layered on top, they have absorption lines from atoms in their atmospheres. So you can think of a star's light as a smooth curve with fine fingerprints. Here is a quiet, everyday example of the temperature shift. Picture a stove coil heating up. At first, it is hot, but it does not glow visibly. It is radiating mostly in infrared. As it heats more, it begins to glow a dull red. That means some emission has shifted into the red end of visible light. If it becomes even hotter, it can glow brighter and move toward orange and yellow. At very high temperatures, objects can look white-hot. White-hot does not mean one color. It means a strong spread across many visible wavelengths. So color can be a thermometer if you know the rough map. You do not need math to feel the point. Heat changes the language of light. Now let's return to thermal cameras because they show this idea clearly. A thermal camera measures infrared intensity across a scene. Then it maps those intensities into a visible palette so humans can see differences. The colors in a thermal image are not real colors of the objects. They are a translation choice made by the device or software. One camera may show warmer areas as white. Another may show warmer areas as yellow or red. The important part is contrast and pattern, not the exact hue. If you ever look at thermal images, a calm rule helps. Focus on relative differences, not dramatic interpretation. Warm areas are not automatically dangerous. Cool areas are not automatically safe. It is simply a map of infrared emission at that moment. Thermal images also have a quiet complication called emissivity. Emissivity describes how efficiently a surface emits infrared compared with an ideal blackbody. Matte, dark, non-metal surfaces often have high emissivity. Shiny metals often have lower emissivity and can reflect infrared from other things. So a shiny kettle can look cooler than it really is because it reflects the room. A thermal camera can be fooled by reflections, just like your eyes can be fooled by mirrors. This is why thermal measurements often include emissivity settings or careful calibration. In a casual view, you can just remember this. Shiny surfaces are tricky. Matte surfaces tell a more direct story. Another surprise is glass. Many kinds of glass are transparent to visible light but block some infrared bands. So a window can look like a barrier in a thermal image. You might see cold glass, even if you can see warm objects behind it. That is not a camera mistake. It is the material filtering infrared differently than visible light. So the world looks different in infrared because materials have different rules. Now, infrared is not only for thermal cameras, it also shows up in quiet, everyday technology. Remote controls often use infrared light emitting diodes. The remote sends a pattern of pulses and the device decodes it. You do not see the pulses, but the receiver does. Some phone cameras can faintly see infrared from a remote if you point it at the lens. That is because camera sensors can be sensitive to near infrared. Many devices include filters to block infrared for better color accuracy. But a little often leaks through, enough to notice in a simple test. Infrared is also used in motion sensors. Some motion sensors detect changes in infrared patterns in a room. A warm body moving across the sensor's view can create a change that triggers detection. Other sensors actively emit infrared and measure reflection. Either way, infrared becomes a quiet way to sense presence without visible light. In some smartphones and cameras, near infrared can help with depth sensing. A device can project an infrared pattern and measure how it returns. Or it can use infrared illumination to improve face sensing in low light. The details vary by device, but the idea is steady. Infrared lets systems see structure when visible light is limited. Now we deepen the story into chemistry. Infrared spectroscopy is one of the most powerful uses of infrared light. Many molecules absorb infrared at specific frequencies. Those frequencies correspond to vibrations and rotations inside the molecule. In a simple image, molecules can wiggle in distinct ways. A bond can stretch like a spring. A group of atoms can bend like a hinge. Each kind of motion has a preferred rhythm. When infrared light matches that rhythm, it can be absorbed. So an infrared spectrum becomes a fingerprint of chemical structure. This is used in labs to identify unknown compounds. It is used in atmospheric science to study gases. It can even be used in medical contexts, like analyzing breath for certain molecules. In astronomy, infrared spectroscopy can reveal the composition of distant clouds and planets, all from light collected at a distance. That is quiet wonder, identification without touching. Now, a practical link to the air around you. Carbon dioxide and water vapor absorb specific infrared bands. They do not absorb all infrared equally. They absorb in particular ranges where their molecular motions match the light. This selective absorption matters for how Earth retains heat. It also matters for remote sensing, because some infrared windows are clearer than others. So the atmosphere is not just a blanket. It is a patterned filter with specific absorption lines and bands. That pattern is one reason space telescopes are helpful for infrared astronomy. Water vapor in the atmosphere blocks parts of the infrared range strongly, so ground-based infrared observing often needs dry, high-altitude sites. And for some wavelengths, it needs space. Now, infrared astronomy shows us things visible light cannot. Dust in space can block visible starlight, hiding what is behind it. But that dust often warms slightly and emits infrared. So infrared can reveal star-forming regions wrapped in dust clouds. It can show cooler stars that do not shine strongly in visible light. It can also reveal galaxies whose light has been stretched by cosmic expansion. As the universe expands, light from distant galaxies shifts toward longer wavelengths. Visible light can slide into infrared by the time it reaches us. So infrared telescopes can see very distant, very early galaxies. We will return later to this idea of redshift and stretching space-time. For now, keep it as a soft thread. Infrared can be both warmth and history. It shows the heat of ordinary things, and it shows the ancient light of faraway things. So infrared is the universe's soft signature of temperature and dust. It is a calm bridge between what you see and what you feel. Next, we move to ultraviolet. It is still sunlight, but with enough photon energy to start chemistry and make hidden patterns glow. Ultraviolet light sits just beyond the violet end of visible color. Its wavelengths are shorter than violet, and its photons carry more energy. That rising photon energy is the main reason ultraviolet matters for chemistry. Ultraviolet is often grouped into three bands: UVA, UVB, and UVC. You can think of them as steps upward in energy. UVA is the gentlest of the three, though still beyond visible light. UVB is stronger per photon and is more likely to cause sunburn effects. UVC is stronger still, and it is mostly blocked by Earth's atmosphere. These labels are practical, not perfect borders, but they help us speak clearly about what reaches the ground. For sunlight at Earth's surface, UVA is usually the largest portion of ultraviolet you receive. UVB reaches the ground too, but it is more strongly filtered by air and ozone. UVC is mostly absorbed high above before it can reach your skin. So the atmosphere acts like an active optical filter, not an empty window. Now, a calm, practical tool many weather apps mention is the UV index. The UV index is a simple summary of ultraviolet intensity at the surface. It is weighted toward the wavelengths that are most effective at causing sunburn. So it is not a full physics report. It is a human-centered safety index. If you see it rise at midday, that is the sun's geometry and the atmosphere working together. When the sun is higher, the light travels through less air to reach you. Less air means less filtering. So UV tends to be stronger around midday than early morning or late afternoon. Altitude also matters. At higher elevations, there is less atmosphere above you. That can mean stronger UV levels compared with sea level. Snow, sand, and water can reflect UV as well as visible light. So surface conditions can change exposure quietly and without warning. Now, sunburn is often described like a heat burn, but it is not heat. Sunburn is mainly a photon energy story. UVB photons can damage molecules in skin cells. In particular, they can disturb DNA, the genetic material inside cells. Your body responds with inflammation, which shows up as redness and tenderness. So the burn feeling is your immune system responding to cellular stress. It is not that the sunlight is hot. It is that the photons carried enough energy to trigger chemical change. UVA can also affect skin, but it tends to penetrate deeper and cause different kinds of damage. Both bands matter, and both are part of why moderation is useful. Now we bring in a calming piece of balance. Ultraviolet is not only harm, it can also play a role in useful biology. UVB helps trigger vitamin D production in skin. The body uses ultraviolet as a signal to start a chemical pathway. Vitamin D then supports several processes, including bone health. So sunlight has a biological edge that can be helpful. The calm framing is this: benefits and risks both exist, and timing and moderation matter more than fear. Short, regular exposure can be different from long, intense exposure. Skin type matters. Location matters. Season matters. And your body has defenses as well. Cells have repair pathways that can fix some forms of DNA damage. Repair is not perfect, but it is real and active. That is one reason the body can tolerate small exposures. Still, there is no prize for pushing beyond your skin's limits. It is reasonable to use shade, clothing, and sunscreen as tools. And sunscreen is best understood as a filter, not a force field. It reduces how much ultraviolet reaches your cells. It does not make you invulnerable. Reapplication and coverage matter, because filters only work where they are present. Now, ultraviolet has another gentle wonder: fluorescence. Fluorescence happens when a material absorbs higher energy light and then emits lower energy light. Often it absorbs ultraviolet and emits visible light. So something invisible in becomes something visible out. The emitted light has longer wavelength, which is lower energy per photon. The difference in energy becomes small amounts of heat or internal vibration. Then the rest leaves as a soft, visible glow. Many minerals fluoresce under ultraviolet. Some biological tissues can fluoresce too, in subtle ways. You may have seen novelty lights that make certain objects glow. A classic example is tonic water. Tonic water can glow under ultraviolet because it contains quinine. Quinine absorbs ultraviolet and re-emits visible blue light. The glow can look calm and ghostly, like a soft neon. It is not radioactive. It is simply energy being shifted from one wavelength range to another. This idea will return later when we talk about X-ray detectors. Some X-ray screens use materials that fluoresce, turning X-ray energy into visible flashes. So fluorescence is a bridge between unseen and seen. Now return to the atmosphere again, because it is central to ultraviolet life on Earth. Ozone in the stratosphere absorbs much of the sun's UVC and a large share of UVB. This absorption is a protective layer for surface organisms. It is not a solid shield. It is a chemical region that intercepts certain wavelengths effectively. So when we say the ozone layer, we mean a zone where ozone is concentrated enough to matter. Its presence shapes what kinds of sunlight reach forests, oceans, and skin. This is why changes in ozone have been treated as important for public health and ecosystems. It is also why some places and seasons experience higher UV risk. The filter is not uniform everywhere all the time. Now we move to a controlled use of ultraviolet where the energy is useful. UVC can be used for disinfection in design settings. Because UVC is energetic, it can damage the genetic material of microbes. That can prevent them from reproducing. So UVC can reduce bacteria and viruses on surfaces or in airstreams. but it only works well where the light reaches. Shadows matter because UVC is line of sight. A surface in shade may receive a much smaller dose. Time matters as well. Disinfection depends on dose, which is intensity multiplied by exposure time. Different organisms require different doses to be effectively inactivated. So UVC is not a magical sweep. It is a careful method used with design and testing. A gentle safety note fits here. Because UVC can harm skin and eyes, it is used with shielding and interlocks. Good systems rely on protective design, not on people being perfectly careful. So the calm approach is respect and structure, not panic. Now we return to life that uses ultraviolet in quiet, beautiful ways. Many insects see ultraviolet patterns on flowers. Some flowers have nectar guides that are visible in ultraviolet but not in human vision. To a bee, the flower can have a bold target-like pattern pointing to food. So ultraviolet can be part of a communication channel between plant and pollinator. Some birds can see ultraviolet too. Plumage that looks plain to us can have ultraviolet contrast to another bird. That can influence mating signals and social cues. So two creatures can look at the same scene and see different information. Some reef organisms also show fluorescence under blue and ultraviolet light. Corals can glow with greens and reds that are not present under ordinary lighting. The glow can come from proteins that absorb one color and emit another. In the ocean, this can be part of protection, signaling, or energy handling, depending on species. Even deep sea creatures can use small amounts of bioluminescent and fluorescent light. Nature is full of hidden light channels layered on top of the visible world. Here is a tiny curiosity loop to keep you softly engaged. If flowers have ultraviolet patterns you cannot see, what else in your room might look different in ultraviolet? Some fabrics, papers, and detergents can fluoresce. Some old tapes and glues can glow faintly. Even fingerprints can sometimes show differently under ultraviolet. You do not need to test it tonight. Just let the thought hang as a quiet possibility. Ultraviolet is the sun's chemical edge. It is energetic enough to reshape molecules. It can support useful biology, and it can also cause cellular stress. It can make invisible patterns visible through fluorescence. And it is filtered by the atmosphere in a way that makes surface life possible. Before we go higher in energy, we will take a short reset. Then we will enter X-rays, where light starts to pass through soft tissue and reveal structure. Let's take another gentle reset, just to keep the rhythm smooth. You do not need to move, unless you want to. If your shoulders are tense, let them drop a little. If your jaw is tight, loosen it, as if you are about to yawn. Now, give your attention a quiet choice. Pick the next chapter in your mind. X-rays for hidden structure or space for distant light. You do not need to decide out loud. Just notice which word feels calmer when you hear it. If your mind picks one, let it be enough. If it does not pick, that is fine too. This is not a test. It is a soft way to rejoin the story. In long listening, these small decision points help the brain stay oriented. They reduce the need to chase novelty because you already have a direction. Now take one slow breath in and one slow breath out. And let the room stay quiet around you. All right, let's go with X-rays now. Light with short wavelengths and practical ways of seeing inside things. X-rays sit above ultraviolet on the spectrum with much shorter wavelengths. Shorter wavelength means higher photon energy, and higher photon energy changes how light interacts with matter. X-rays can pass through many materials that visible light cannot. That is why we often describe X-rays as seeing through, but it is more precise to say they are absorbed differently by different materials. An X-ray image is a story of absorption and survival. Some photons make it through, and some are removed along the way. Thickness matters as much as composition. A thin sheet of a dense material can block strongly. A thicker layer of a lighter material can also block, simply by giving more chances to interact. So penetration is not a single property of the beam or the object. It is a relationship between energy, material, and path length. In general, Denser materials absorb more X-rays than less dense materials, and materials with higher atomic number tend to absorb more strongly as well. This is part of why bone stands out in an X-ray image. Bone contains calcium, and it is denser than most soft tissue, so more X-ray photons are absorbed in bone. Soft tissue often lets more photons pass through. On a detector, that difference becomes contrast. Light areas often correspond to higher absorption, where fewer photons reach the detector. Darker areas often correspond to lower absorption, where more photons arrived. So an X-ray is not showing light bouncing off the surface. It is showing what remains after the beam traveled through. Now a gentle check-in. Did you picture X-rays as a kind of magical sight? Hold the thought of seeing through, but keep the mechanism grounded. It is selective absorption, not a secret camera vision. Now, how do we make X-rays in the first place? A common method is to accelerate electrons to high speeds, then stop them suddenly. When a charged particle changes speed quickly, it can emit electromagnetic radiation. In an X-ray tube, electrons are released from a heated source. Then a high voltage accelerates them toward a metal target. They slam into the target, and their sudden slowdown produces X-rays. This braking radiation is called bremsstrahlung. It forms a broad spectrum of X-ray energies, not just one line. Some electrons also knock inner electrons out of atoms in the target. When that happens, outer electrons fall inward to fill the gap. Those transitions emit X-rays with specific energies. These are called characteristic X-rays because they depend on the target material. So an X-ray tube can produce both a broad background and sharper spectral lines. The beam is then shaped and controlled. Filters can remove lower energy X-rays that would be absorbed in skin without improving the image. Collimation narrows the beam to the region of interest. This reduces stray radiation and improves contrast. So modern X-ray use is often about careful shaping, not brute force. Now, medical imaging is the most familiar example. A basic radiograph is a single projection like a shadow made with X-rays. The beam passes through the body, and a detector records what arrives. The result compresses three-dimensional anatomy into a two-dimensional image. That can be enough for many uses, like checking bones or chest structure. But sometimes you want depth, not just overlap. This is where computed tomography, often called CT, comes in. In CT, the system takes many X-ray measurements from many angles. Then a computer reconstructs a cross-sectional view. It is like unfolding a three-dimensional object into thin slices. You can think of it as looking at the body layer by layer. The reconstruction relies on mathematics, but the intuition is simple. Many angles reduce ambiguity and separate overlapping structures. CT can show soft tissue differences more clearly than a single projection. Sometimes doctors use contrast agents to enhance certain areas. A contrast agent changes absorption intentionally. For example, iodine-based agents absorb X-rays strongly and can outline blood vessels or organs. Barium can outline parts of the digestive tract. So the image can be guided by chemistry, not only anatomy. Now, a calm framing about dose. X-rays are ionizing radiation, so dose matters. In medicine, dose is measured, optimized, and chosen for the situation. The goal is to get the needed information with the lowest reasonable exposure. Different exams have different typical dose ranges. A small dental image is not the same as a full-body CT scan, and medical decisions depend on benefits and risks together. That is why radiology uses protocols, shielding when appropriate and careful justification. The calm point is not fear. The calm point is that X-ray use is deliberate and controlled. Now we step away from bodies and into crystals. X-rays have wavelengths comparable to distances between atoms and solids. That makes them perfect for probing atomic spacing. This is the heart of X-ray crystallography. If you shine X-rays through a crystal, the atoms act like a regular array of scattering centers. The scattered waves interfere with one another. At certain angles, they reinforce and create bright spots on a detector. This is diffraction. and it is a quiet geometric effect. A simple rule called Bragg's law connects the angle of reflection to the spacing between layers in the crystal. You do not need the formula to feel it. Regular spacing creates regular patterns. From those patterns, scientists can infer the arrangement of atoms. This has been used to reveal mineral structures and metal alloys. It has also been used to map complex biological molecules, including many proteins. In a calm way, invisible waves can map the invisible world. You cannot see atoms with your eyes, but you can see the pattern they impose on X-rays. Then you can reconstruct what must have been there to create it. It is one of the most elegant uses of light as measurement. Now consider industry and security, where inspection without opening is valuable. Industrial radiography uses X-rays to check welds and materials. A beam can pass through a metal part and reveal internal cracks or voids. That helps ensure integrity without destroying the object. The energies used can differ from medical settings, depending on thickness and material. The principles are the same: absorption, contrast, and careful control. In airports, X-ray imaging is used for baggage screening. The goal is to see shapes and materials inside luggage without opening it. Systems use different energy techniques and processing to highlight different densities. Standards and protocols matter here, because safety and reliability depend on design. Again, the calm framing is structure and regulation, not mystery. X-rays are powerful tools, and power is managed with rules. Now we lift our gaze to the sky again. X-ray astronomy exists because the universe has very hot and very energetic places. Hot plasmas at millions of degrees emit X-rays. Supernova remnants can glow in X-rays as shock waves heat surrounding gas. Near black holes and neutron stars, matter can be accelerated and heated to extreme temperatures. Accretion disks can shine strongly in X-rays. So X-rays can reveal environments that are invisible in visible light. But there is a reason you do not see X-rays from space with your eyes on Earth. Earth's atmosphere blocks most X-rays. That is good for life. It protects surface biology from a constant bath of high-energy radiation. For astronomy, it means X-ray telescopes must be placed above the atmosphere. So we use satellites and space observatories to capture those photons. Their detectors often work differently than optical cameras. Some convert X-rays into small flashes of visible light inside special materials. Some directly measure the energy deposited by each photon. Either way, the aim is the same: translate X-rays into data we can read. Now hold the gentle check-in as we prepare for the next step. If X-rays are a doorway to high-energy light, gamma rays go deeper still. They often come from nuclei and the most extreme cosmic events. That origin story is what changes next. Gamma rays sit at the high-energy end of the electromagnetic spectrum. They have very short wavelengths and very energetic photons. In everyday speech, gamma rays can sound intense. But the calm truth is that context matters more than the word itself. A gamma ray is defined as light with a certain range of high energies. Often it is produced in nuclear transitions when an atomic nucleus changes state. It can also be produced when energetic particles interact and release photons. The line between high-energy X-rays and lower-energy gamma rays can blur in practice. Sometimes the distinction is based on origin rather than a strict energy cutoff. X-rays are often linked to electron processes, like X-ray tubes and atomic shells. Gamma rays are often linked to nuclear processes and particle physics events. Either way, we are still talking about photons. The difference is how much energy each photon carries and where it came from. Because gamma photons are energetic, they can penetrate deeply into materials. But penetrating does not mean unstoppable. It means the probability of absorption is lower per unit thickness for many materials. So you need more thickness, more density, or different strategies to reduce exposure. Shielding is a story of chances. Each layer gives a photon an opportunity to scatter or be absorbed. Dense materials like lead provide many electrons and nuclei in a small volume. That increases interaction probability in a given thickness. Concrete can also be effective, especially when used thickly and broadly. The practical idea is simple. To reduce gamma exposure, You often use time, distance, and shielding. Spend less time near a source, increase your distance, and place dense material in between when needed. Now we step into the idea of background, which is gentle and real. Gamma rays exist naturally in small amounts around us. Some rocks contain natural radioisotopes. Building materials can contain trace amounts too. So there is a measurable baseline of radiation in most places. That baseline varies by location. Areas with more uranium-rich rock can have higher natural background. Some places with granite, for example, can show slightly different levels. Altitude can also change exposure a bit. Higher altitude means less atmosphere above you. The atmosphere blocks and moderates some incoming cosmic radiation. So at high altitude, you can get a slightly higher dose from cosmic sources. This is also why airline crews can receive higher average exposure than people who never fly. Again, this is about baseline differences, not sudden danger. Think of background like a quiet hum in the room. It is present and it is measurable, but it is not usually dramatic. Some of that background comes from cosmic rays. Cosmic rays are high-energy particles arriving from space. When they hit the atmosphere, they create showers of secondary particles. Those interactions can produce gamma photons among other products. So the sky contributes a little to the background you live inside. The Earth contributes a little. And even your own body contains small amounts of naturally occurring radioisotopes. So radiation is not a foreign intruder. It is part of the environment at low levels all the time. Now, gamma rays also have controlled medical uses. One important example is positron emission tomography, often called PET. PET imaging uses a tracer that emits positrons. A positron is the antimatter partner of an electron. When a positron meets an electron, they annihilate. Annihilation is a conversion of mass into energy. In this case, it often produces 2 gamma photons. Those 2 photons fly off in nearly opposite directions. A PET scanner surrounds the patient with detectors. When 2 detectors register photons at nearly the same time, that is called coincidence detection. The system assumes those 2 photons came from one annihilation event along a line between detectors. With many events, the scanner reconstructs where the tracer is concentrated. So PET turns gamma photons into a map of metabolic activity. It is controlled, purposeful, and designed with dose management in mind. Often, PET is paired with KT to align activity with anatomy. So different parts of the spectrum can work together in one medical tool. Now we move back out to the universe, where gamma rays can be messages from extremes. Gamma ray astronomy studies the highest energy photons from space. Because Earth's atmosphere blocks most gamma rays, detectors must be above the atmosphere. Gamma detectors are not like optical telescopes with simple lenses. Gamma rays can pass through ordinary glass and mirrors. So the detectors often rely on interactions inside dense materials. A gamma photon might scatter in a detector and deposit energy. That energy can create a flash of light inside a scintillator material, or it can create charge in semiconductor detectors. Either way, the instrument counts events and measures energy and direction indirectly. Gamma ray sources include active galaxies with jets. Near some supermassive black holes, particles are accelerated to extreme energies. Those particles can produce gamma photons through collisions and radiation processes. Supernova remnants can also accelerate particles in shock waves. Those particles can then generate gamma rays when they interact with surrounding gas and light. So gamma rays can trace cosmic particle accelerators. One of the most dramatic gamma events is a gamma ray burst. A gamma ray burst is a brief, intense flash of gamma photons from very far away. Many are linked to the collapse of massive stars or to mergers of dense objects. They can last from fractions of a second to minutes. Then they fade, leaving afterglows at lower energies. Even though the bursts are intense at the source, they are incredibly distant. By the time they reach us, they are detectable mostly as faint signals collected carefully. So again, context matters. The word burst does not mean the sky is close to you. It means the source released energy quickly, far away. Now, how do gamma rays interact with matter? Several pathways matter, and we can keep them gentle. One major process is Compton scattering. In Compton scattering, a gamma photon hits an electron and transfers some energy. The photon changes direction and loses energy. The electron recoils and carries away the difference. This is part of why gamma rays can penetrate, yet still be detected. They can scatter multiple times before being absorbed completely. Another process at higher energies is pair production. In pair production, a gamma photon can transform into an electron and a positron. This requires enough energy and usually happens near a nucleus that helps conserve momentum. The resulting particles then slow down, interacting with matter in other ways. Eventually, the positron can meet an electron and annihilate, producing more gamma photons. So gamma rays can set off a small cascade of interactions. Still, these interactions follow rules and probabilities. They are not mystical forces. This leads back to shielding strategies. Because scattering is common, thickness helps. Because intensity drops with distance, distance helps. And because dose accumulates over time, limiting time helps. So the classic trio, time, distance, and shielding, is not a slogan. It is a real summary of how interaction probabilities work. Now we return to the emotional side for a moment, calmly. Does the word gamma feel intense because of stories you have heard? If it does, that is normal. Many words gather drama from movies and headlines, but we can replace story with structure. Gamma rays are high-energy photons. They are produced in certain nuclear and cosmic processes. They can be harmful at high doses or close proximity. They can also be useful when controlled, measured, and justified. Units and limits exist to keep exposures low. Professionals use monitoring and protocols in medical and industrial settings. And most of the gamma rays you encounter in daily life are part of a low background baseline. So the calm perspective is clarity without alarm. Now we have climbed to the top of the spectrum. We have met the highest energy photons. Next, we return to the central mystery that ties all of this together. How can light behave like a smooth wave and like counted particles, depending on how you ask the question? That is where we go next. We have climbed the spectrum from slow radio to sharp gamma. Now we shift to a different kind of map, the map of behavior. Quantum light is not a new kind of light. It is what ordinary light looks like when you ask very small questions. At small scales, light can arrive in countable packets. Those packets are called photons. You can picture photons as individual deliveries of energy. Not a steady pour, but a series of discrete drops. This does not cancel the wave picture. It adds a second layer that becomes important in certain experiments. A calm place to begin is the photoelectric effect. Imagine a clean metal surface in a vacuum. Shine light on it, and sometimes electrons come out. The surprising detail is what controls that release. It is not only how bright the light is, it is also the light's frequency, what we informally call its color. For some metals, no electrons come out below a certain frequency. You can increase brightness and still get nothing. Then you raise the frequency and electrons appear. That minimum is called a threshold frequency. It is like a key that must fit before a door can open. Below the threshold, the energy per photon is too small. Above the threshold, each photon can carry enough energy to free an electron. So some effects depend on photon energy, not total power. This is the quiet lesson. Brightness and color are not the same lever. Brightness is how many photons arrive per second. Color, or frequency, sets how much energy each photon brings. Now picture two flashlights, one red and one ultraviolet. A bright red light can deliver lots of total energy. But each red photon is relatively gentle. A dim ultraviolet light can deliver less total energy, but each ultraviolet photon can be more energetic. For the photoelectric effect, that per photon energy is what matters. So dim ultraviolet can do what bright red cannot in that specific setup. That is not a poetic statement. It is a testable outcome seen in labs for over a century. It also explains why the ejected electrons have a certain maximum energy. Higher frequency light can produce faster electrons. Not because it is brighter, but because each photon carries more energy. If you raise brightness at the same frequency, you mainly get more electrons. If you raise frequency, you change the energy available per event. So energy arrives in steps, not as an infinitely divisible drizzle. That is the calm aha at the center of quantum light. Now we move to another experiment with a different mood, the double slit. It is simple in shape, but deep in meaning. You send light toward a barrier with two narrow openings. Behind it, you place a screen that records where light arrives. If light were only particles like tiny pellets, you might expect two bright bands. One band from each slit, like two overlapping shadows. But with ordinary light, you see an interference pattern. Bright and dim stripes appear across the screen. That stripe pattern is what waves do when they overlap. Where the waves reinforce, the screen is brighter. Where they cancel, the screen is dimmer. So the two slits behave like two wave sources. Their overlap draws a repeating pattern in space. Now here is the gentle twist. You can lower the light until it is extremely faint. So faint that photons arrive one at a time. The screen no longer brightens smoothly. It records individual dots, one dot per detected photon. At first, the dots look scattered and random, but over time, a pattern emerges. The dots build up into the same interference fringes. So each detection is particle-like, a single localized event. Yet the overall distribution is wave-like, a pattern of highs and lows. A calm way to say it is this: the probability of arrival behaves like a wave. The photon lands as a dot, but the dot is drawn from a wave-shaped probability. This is why people say light is wave and particle. It spreads like a wave in its likelihood. It arrives like a particle in its detection. Now we add a key detail without drama. If you try to learn which slit the photon went through, the fringes disappear. When which path information is available, interference is reduced or removed. The dots still appear, but the stripe pattern fades. It becomes more like two blurred bands, not a fine fringe pattern. This is not because observation is magical. It is because the measurement setup changes what can interfere. To preserve fringes, the two paths must remain coherent, meaning phase-related. When you mark the path, you disturb that coherence. So the outcome depends on the question you ask and how you ask it. This is why quantum stories can feel philosophical, but the core is practical. Different setups produce different statistics. Now we move to uncertainty, which can be calming when framed gently. Quantum uncertainty is not mainly about imperfect tools. It is a feature of how nature encodes information at small scales. Some pairs of properties have built-in trade-offs. A famous pair is position and momentum. If you pin down position very tightly, momentum becomes less sharply defined. If you pin down momentum very tightly, position becomes less sharply defined. This is not a penalty for curiosity. It comes from the mathematics of waves and localization. A tightly localized wave packet needs many wavelengths to build it. Many wavelengths correspond to a spread in momentum. So uncertainty is linked to the wave-like description itself. It tells you that perfect prediction has natural limits. And that can be comforting, because perfection is not required. Nature already includes softness at the edges. Uncertainty also helps explain why atoms are stable. If electrons were tiny planets on crisp orbits, they would lose energy and spiral inward. They would radiate and matter would collapse. Instead, electrons occupy quantum states. Those states are more like standing wave patterns than like orbits. A standing wave has a stable structure with allowed energies. So, an atom is not a miniature solar system. It is a structured set of probabilities that remain steady in time. This structure prevents collapse and allows chemistry to exist. So uncertainty is not chaos. It is part of the scaffolding that makes solid matter possible. Now we return to how atoms trade light. Atoms and molecules absorb and emit photons in selective amounts. They do not accept any energy you offer. They prefer energies that match the gaps between allowed levels. If the photon energy matches a gap, absorption is likely. If it does not, the photon often passes through. When an atom falls from a higher level to a lower one, it can emit a photon. Because the levels are discrete, the emitted photons have specific energies. Those specific energies show up as spectral lines. Spectral lines are like fingerprints for elements and molecules. In a lab, you can identify substances by their line patterns. In astronomy, you can identify elements in stars by the same method. A star spectrum often looks like a smooth curve with thin missing lines. Those missing lines are absorption, where certain wavelengths were removed by gases. A glowing gas cloud can show bright emission lines instead. So light carries the identity of matter across great distances. This is one of the quiet miracles of physics, recognition without touch. Now connect this to a familiar object, a neon sign. Neon signs glow with a distinctive hue because of atomic transitions. Electrons in neon atoms are excited, then they drop and emit photons. Other gases, like argon or mercury vapor, produce other characteristic colors. So the color is not paint. It is the energy structure of the atoms making light. Now we place a small marker for later, because it leads to lasers. There are two broad ways emission happens: spontaneous and stimulated. Spontaneous emission happens when an excited atom emits without prompting. The timing is random within a predictable probability. The direction is random and the phase is not coordinated. That makes ordinary glowing light warm and scattered. Stimulated emission is different. In stimulated emission, an incoming photon encounters an excited atom. That photon can encourage the atom to emit another photon, and the emitted photon matches the incoming one in frequency and direction. It is like a gentle copy aligned with the original. This matching is the bridge to coherent light. We will use it soon when we talk about lasers. Now, entanglement, stated calmly and carefully. Entanglement is a way two quantum systems can share a joint description. Their properties can be linked in a way that cannot be reduced to separate parts. When you measure one, the statistics for the other are constrained, even if the two are far apart. This can sound like instant influence, but it is not a messaging channel. You cannot use entanglement to send information faster than light. The outcomes you see are not under your control. You only observe them, one by one. The striking part is the correlation pattern across many trials. When the results are compared later, the links appear clearly. Those correlation patterns are tightly tested in experiments. They have been confirmed with careful controls and modern detectors. Entanglement matters because it can be useful. It can improve precision in certain measurement strategies. It can support secure communication protocols where eavesdropping changes the statistics, and it can enable quantum networking demonstrations and timing experiments. Still, it remains grounded in ordinary rules. No faster than light signaling is gained. So the calm takeaway is this: entanglement is strong correlation, not secret telepathy. Now we bring quantum light into everyday technology. A camera sensor is, in a quiet way, a photon counting device. In bright light, it receives huge numbers of photons each moment. The count is so large that the image looks smooth. In dim light, the count becomes small enough to feel grainy. That graininess is not only electronics noise, it is also shot noise, the randomness of discrete arrivals. If you double the light, you do not get exactly double the counts every instant. You get an average doubling with fluctuations around it. Those fluctuations are part of the physics of counting events. This is why cameras struggle in extreme low light. There are simply not enough photons to describe fine detail reliably. Some detectors are built to notice single photons more directly. Avalanche photodiodes can amplify a single photon event into a larger pulse. Photomultiplier tubes can do something similar using cascades of electrons. These tools turn a tiny quantum event into a measurable signal. They are used in labs, telescopes, and medical detectors. In some experiments, scientists count photons and measure their arrival times. They look for time correlations between events. This helps separate real signals from background noise. It also helps test quantum predictions about correlations and interference. So quantum light is not only about strange thought experiments, it is the working language of precision detection. Now return briefly to the double slit idea with a softer angle. You can think of the wave function as a recipe for probabilities. It does not tell you exactly where one photon will land. It tells you how likely each landing region is. Over many photons, the recipe becomes visible as a pattern, so the world can be uncertain in detail, yet reliable in statistics. That is a nice balance for a tired mind. It says you do not need perfect prediction to have stable structure. Now, a gentle reflection prompt with no need to answer, which felt more intuitive. Waves, particles, or both depending on the question. If you leaned toward waves, you may like interference and patterns. If you leaned toward particles, you may like thresholds and counted events. If you lean toward both, you are in good company. Physics uses whichever picture fits the measurement best. Now we open the loop toward lasers more clearly. Lasers are not mystical beams. They are light made orderly through stimulated emission and feedback. Order means many photons matching in frequency, direction, and phase relationship. That matching produces coherence, a special kind of sameness over time and space. Coherent light can be aimed, focused, and controlled with great precision. It can also carry information calmly over long distances in fiber optics. So the quantum story is not separate from the everyday world. It is the foundation under modern communication and measurement. With quantum behavior in hand, lasers become less mysterious. They are organized light, shaped for precision and calm reliability. And that is where we drift next, into coherent beams and gentle order. Let's make the next hour feel a little smoother with one small setting. If you are still awake, set a sleep timer for about 30 to 45 minutes. That way, you can keep listening without wondering when to stop. Then lower your screen brightness one more step, even if you are not watching. Small light changes can make a room feel quieter. If your phone is face up, consider turning it face down again. Now, if you feel like leaving a tiny breadcrumb for future episodes, you can do this. Type just one number in the comments. Type 1 if you want more biology. Type 2 if you want more space. No explanation needed, just a single digit. And if you do not want to type anything, that is perfectly fine. The goal is comfort, not effort. All right, next, lasers, light that is unusually tidy and useful because it stays steady. A laser is a light source with unusually tidy behavior. A lamp spreads light in many directions at once. A laser sends light mostly in one direction, as a narrow beam. That directional beam spreads less, so more light stays together over distance. Another difference is spectrum. Most lamps produce a broad mix of wavelengths. Many lasers produce a much narrower range, closer to a single color. And the deepest difference is coherence. Coherence means the light waves are aligned in a consistent phase relationship. In ordinary light, phases are jumbled and shift rapidly. In coherent light, the wave pattern stays organized for longer. These properties matter because order can be used. It can be aimed, measured, and carried through narrow paths. It can also encode information in a clean and stable way. Now, a quiet visualization. Picture a beam as a straight, steady line. Then imagine that line guided inside a hair-thin glass thread across an ocean. That is not science fiction. That is how much of modern communication works. To understand lasers, we return to the quantum bridge we opened. The engine is stimulated emission. Begin with atoms or molecules that have stored energy. They are in an excited state, ready to drop down to a lower state. When they drop, they can release that energy as a photon. If they drop on their own, that is spontaneous emission. The photon leaves in a random direction with a random phase. That makes ordinary glow, scattered, and warm. Stimulated emission is different. If a photon passes by with the right energy, it can trigger emission. The excited atom releases a second photon that matches the first. Same frequency, same direction, and a related phase. So one photon becomes two in a neatly aligned pair. That is amplification, but in the language of light. To get strong amplification, you need many excited atoms ready at once. This is the idea of population inversion. Normally, most atoms sit in the lowest energy state. A laser needs the upper state to be unusually populated, so the system is pumped. meaning energy is added to lift atoms upward. The pump can be an electric current, another light source, or chemical energy. Once enough atoms are excited, a passing photon can trigger a cascade. Now the light builds, and it builds in an orderly way. A laser also uses a cavity, often made with mirrors. Two mirrors facing each other let light bounce back and forth through the gain medium. The gain medium is the material where stimulated emission occurs. Each pass through the medium can amplify the light. The mirrors also select which waves survive. Only certain standing wave patterns fit the cavity well. Those are called modes, and they are like stable notes in a resonant instrument. One mirror is usually partially transparent, so a small fraction of the organized light escapes as the output beam. That escaping beam is what you see as the laser. So a laser is not a single event. It is a feedback system that encourages order. Now lasers come in many types, and we can group them gently. Some are continuous, meaning they produce a steady beam over time. Some are pulsed, meaning they produce bursts separated by quiet intervals. A pulsed laser can be intense in peak power, even if the average power is modest. That is because energy is concentrated into short moments. You do not need drama to understand this. It is like saving up small amounts and releasing them together. Pulses can be useful for timing and measurement. Continuous beams can be useful for stable alignment and communication. There are gas lasers, where the gain medium is a gas in a tube. There are solid-state lasers, where the gain medium is a crystal or glass. There are semiconductor lasers, which use tiny structures like those in electronics. There are fiber lasers, where the gain medium is inside an optical fiber. What changes between these types is the material, the pumping method, and the cavity design. But the core engine is the same: stimulated emission and feedback. Many everyday devices have used small lasers. Barcode scanners use them for reading patterns reliably. Optical disk drives use lasers to read and write tiny pits and marks. Laser pointers are simple examples designed for convenience. In industry, lasers cut, weld, and measure with precision. In medicine, some lasers are used in surgery and eye procedures with careful control. So the word laser covers a family of devices, from gentle to powerful. Now we connect lasers to the quiet highways of fiber optics. Fiber optics guide light through thin strands of glass. They do it using total internal reflection. When light tries to leave a dense material into a less dense one at a shallow angle, it reflects back inside. A fiber is designed with a core and a cladding. The core has a slightly higher refractive index than the cladding. This difference keeps light trapped inside the core. So the light zigzags down the fiber, reflecting along the way. The effect is smooth and efficient, like water guided in a pipe. Fibers have low loss, meaning the light fades slowly over long distances. That is why signals can travel far with only occasional boosting. Across continents and under oceans, fibers carry enormous amounts of data as light. Undersea cables are quiet light highways on the ocean floor. They are physical, not wireless, and they are a major part of global communication. Now, light in a fiber is not perfectly unchanged. One issue is dispersion. Dispersion means different wavelengths travel at slightly different speeds in the fiber. If you send a short pulse that contains a range of wavelengths, it can spread out in time. Over long distances, pulses can blur into one another. Engineers manage this with careful wavelength choices, fiber design, and signal processing. Sometimes they use multiple channels, each at a different wavelength in the same fiber. This is like sending several colored beams down one glass thread. The fiber is quiet, but the information inside it can be vast. Now we move to measurement tools that use coherent light. Coherence makes interference easier to use. An interferometer splits a beam into two paths and then recombines them. If one path changes length by a tiny amount, the interference pattern shifts. This lets interferometers measure extremely small distance changes. It is like measuring with a ruler made of wave cycles. Lasers also support LIDAR, often said as LIDAR. LIDAR measures distance by time of flight. A laser pulse goes out, reflects from a surface, and returns. The travel time reveals distance when you know the speed of light. This is similar to radar, but with much shorter wavelengths. Because wavelengths are shorter, LiDAR can resolve fine details. It can map landscapes, buildings, and forests from aircraft. It can also help vehicles sense the world, depending on the system design. Another precision tool is the frequency comb. A frequency comb is a laser technique that produces a set of very evenly spaced frequencies. It acts like a ruler for light frequencies, with many regular marks. This helps compare optical frequencies to clocks and measure them precisely. The comb connection is simple. Precision does not require loudness. It requires steadiness, repeatability, and careful design. Lasers are valuable because they stay steady and structured. Now, a gentle word about safety and comfort. Laser light can be gentle and still deserve respect. Because laser beams are narrow, they can concentrate light onto a small spot. Your eye can focus a beam onto the retina, making the intensity higher there. So eye safety is not about fear. It is about geometry and focusing. Laser classes exist as practical guidance for safe use. They tell you what kind of exposure is expected to be safe under specified conditions. Another important detail is invisibility. Some lasers emit in infrared, which you cannot see. An invisible beam can still be there, which is why labels and controls matter. In professional settings, safety relies on shielding, interlocks, and training. In everyday life, the calm advice is simple. Do not stare into beams, do not aim them at eyes, and treat powerful devices with caution. Now we open the transition forward. We have taken light and made it orderly. We have guided it in fibers and used it as a measuring tool. Next, we lift our gaze outward. We will talk about how light travels through space, stretches with the universe, and bends around gravity. Now we let light leave the laboratory and move into the big stage, space-time. Light does not only reveal objects, it also reveals how the universe is stitched together. One of the strongest ideas is the speed of light as a limit for information. In relativity, no signal can outrun light in vacuum, so there is no true instant message across space. Every message has travel time. That travel time becomes a tool, not only a limitation. If you can measure how long light takes, you can measure distance. This is the quiet heart of ranging and navigation. It is also a gentle lesson in astronomy. Seeing far is seeing the past. Light from distant objects has been traveling a long time, so telescopes are time machines that only receive, never send. When you look at a faraway galaxy, you are reading an older chapter of that galaxy's life. The farther the object, the older the chapter you are seeing. This makes the night sky feel deep, not just wide. It is not only a picture. It is a layered archive. We can feel this idea in everyday space technology too. Space probes do not talk to Earth in real time. Signals take time to cross the gap. Engineers plan around those delays calmly and precisely. They schedule commands and they wait for confirmation. When a probe is far away, you might send a message and then wait, knowing the universe will deliver it on its own schedule. That delay is not inconvenience. It is a measurement of distance written in minutes and hours. The speed of light also supports our best clocks. Many modern time standards rely on atomic transitions measured with light. Atoms trade photons at extremely stable frequencies. Those frequencies become ticks that define precise time. So light is not just a messenger of events. It is a metronome for civilization. Now we move to color as information about motion and expansion. Light can shift in wavelength. If a source approaches, the light shifts toward shorter wavelengths. If a source recedes, the light shifts toward longer wavelengths. This is the Doppler effect for light. You can remember it as a gentle rule. Toward blue when approaching, toward red when receding. Astronomers measure these shifts by looking at spectral lines. They compare observed lines to known laboratory values. A shift tells motion along the line of sight. This is how we know stars in a galaxy rotate and how we know some stars are moving toward or away from us. But in cosmology, redshift often means something even larger. It is not only motion through space. It is the stretching of space itself. As the universe expands, the distance between distant galaxies grows. Light traveling through that expanding space can be stretched as well. So the wavelength increases during the journey. That is cosmological redshift. It is like a wave drawn on a rubber sheet that is slowly being pulled wider. The wave still moves forward, but its spacing grows as the sheet expands. This connects directly to our infrared chapter. Light that began as visible in a young galaxy can arrive as infrared after traveling across an expanding universe. So infrared telescopes are in part history detectors. They catch ancient starlight that has slid into longer wavelengths. This is one reason distant galaxies and early star formation can appear strongly in infrared surveys. The universe writes travel into color. Now we add gravity as another kind of editor. In general relativity, mass curves space-time. Objects move through that curved geometry, and so does light. Light follows the straightest possible path in curved space-time. From our perspective, that looks like bending. This is gravitational lensing. A calm way to picture it is that gravity acts like a slow, patient lens. A massive galaxy or cluster can bend the light from objects behind it. The background object can appear stretched into arcs. Sometimes you see multiple images of the same object. Sometimes you see a partial ring or a near complete ring. These are not illusions created by the eye. They are geometry made visible. The lens does not create new light. It redirects and magnifies the light that already existed. This can make very distant objects easier to detect. Nature provides its own magnifying glass. Lensing also teaches us about mass we cannot see directly. Some matter emits light, like stars and hot gas. Some matter does not, yet it still bends space-time. So by measuring lensing patterns, astronomers infer where mass must be. Light becomes a probe for invisible distributions. Again, it is translation by interaction. Now we return to the most dependable translator of all, spectra. Spectral fingerprints work because physics is consistent. The same atomic rules apply everywhere we can see. Hydrogen atoms in a distant cloud have the same energy levels as hydrogen here. So their absorption and emission lines match the same patterns. When starlight passes through gas, certain wavelengths are absorbed. That makes dark lines in the spectrum. When gas glows, it can produce bright lines. From these lines, we identify elements at a distance. We also infer conditions. Line shifts reveal motion. Line widths can reflect temperature, pressure, or turbulence. Line ratios can reveal density and ionization states. So, spectrum is not just a pretty rainbow. It is a compact report. Composition, motion, and environment. It is why we can describe stars we will never visit. Now we zoom out to faint fields of light that fill space. These are cosmic backgrounds. A background is not a single object. It is many contributions added together across time. The cosmic microwave background is one example we already met. It is a nearly uniform microwave glow from a very early era. Its tiny variations carry information about early structure. There is also an infrared background built from many dusty galaxies. Dust absorbs energetic light and re-emits in infrared. Over billions of years, that adds up to a faint infrared haze across the sky. So backgrounds are not only noise, they are maps of cumulative history. To study them, detectors and analysts separate layers gently. They model foreground sources like our own galaxy and our local dust. They compare frequencies, because different sources have different spectral shapes. They use statistics to tease out what is steady and universal from what is local and changeable. This is slow science, careful science, not dramatic science. It is pattern recognition with patience. Now we gather the capstone for this chapter. Light is a universal messenger because it travels so well. It carries energy, but it also carries information. It carries timing, direction, and spectra. It can be stretched by expansion and bent by gravity. It can be absorbed and re-emitted, leaving fingerprints behind. From radio whispers to gamma flashes, it is one continuum. Different names are just handles for different uses and detectors. What we cannot see directly, we infer from interactions. We infer from absorption, scattering, emission, and arrival time. And in this video, the 100 facts are really one story. A story of translation from invisible to understandable. From the narrow slice your eyes see to the deep signal space carries. Now, a soothing recap prompt, just for your own mind. If you remember only one equation or one idea, which would you choose? The link between wavelength and frequency, photon energy arriving in steps, or the simple idea that light carries information? No need to decide firmly. Just let one of them feel like a small handle you can hold. Next, we will end softly. We will gather the whole spectrum into a few simple, reusable ideas you can remember tomorrow. If this felt steady and helpful, you can subscribe and keep this kind of calm science close by. For the next long, quiet session, choose a topic in the comments. Type time, oceans, or the brain. Just one word is enough. And if you are drifting off, no worries. You can decide another night.